Hello and welcome to the Champak Induction Challenge Part 2, where we tackle Tuesday's maths problem for the second part. Well, this question involves taking the formula n cubed plus 2n, and it states that we'll have a factor of 3 when n is any integer. Now, we can get right into this using the tape method from before. We can give ourselves a try, and let's just try to start things off. N equals 1, and that will naturally substitute in 1 cubed plus 1 times n, and like before we can substitute a factor of 3 as 3b with b in the set of the any integer. B is any integer. Now, from this, we can solve this as 1 cubed as being, sorry, that's not right, that's going to be 2 times 1. 1 cubed is 1 plus 2, it's going to equal 3b. It's going to equal 3 is 3b, and naturally, because 3 cancels from both sides, 1 equals b, and 1 is an integer, so yeah, that works out. It works for the trial step. Now, we're going to move on to our assumption. So we're going to assume that k cubed plus 2k equals, in this case we can go 3b again, where k is any integer and b is any integer. Now from here we've got our k values, and we can go for our next step. So if remember from before, we want to be able to find this. This is what we want to be able to find when we do our proof step, and because this is already expanded, we can move straight along to our proof. And notice that this problem is significantly easier than the previous one, even though it's the second of the ones that were given out. So prove for n equals k plus 1. So we want to show that k plus 1 cubed plus 2k plus 1, where n was in our original equation, is going to have a factor of 3, and let's use capital A this time just to change things up so we don't have B and A conflicting when we solve this. And again, k is going to be in the set of the integers and A is in the set of the integers. That out of the way, we can start cracking into the proof step of this. Remember to leave the assumption visible so you know what we're trying to tackle here. So bring this down, we're just going to work on this left hand side here. So let's start by just writing this out again. K plus 1 all cubed plus 2k plus 1, and we can expand k plus 1 cubed as k cubed plus 3k squared plus 3k plus 1. So that's that term expanded. Now we can work on the second term, and that's going to come as plus 2k and plus 2. Now, what we're looking for is this term, k cubed plus 2k, and we have a k cubed term, we have a 2k term, so let's just arrange them so they fit together. So it's k cubed plus 2k, and we can just stick on there 3k squared plus 3k got our 1 and our 2's plus 3 because we can just add these two together. Alright, now we can compress these together because we know that 3k cubed plus 2k, sorry, is equal to 3b. So we can write this as 3b plus, well, the second half of this can have 3 factored out of all the terms. 3 factored out of k squared plus k plus 1. And as we continue, we can now substitute this back in to equal our 3a term back over the right hand side, which is just 3a. So this is going to equal 3a, and we can take 3 out the front of both those, so 3 lots of b plus k squared plus k plus 1 equals 3a, and we can cancel our 3 off both these sides, and we get left with b plus k squared plus k plus 1 equals a. And because remember that b is an integer and both of these k's are integers, we know, and we're just adding them together, we know that a is also going to be an integer. And that fulfills our initial condition that this will give us our value here, seen here, 3a, where it's an integer. So this shows that for k plus 1 we do indeed have that factor. Now let's just explain it and finish this off. So explain. Right. Since, get our original equation back, just scroll up there. N cubed plus 2n. N cubed plus 2n has a factor 3 for, well, we tried it for n equals 1, n equals k, and n equals k plus 1, then, therefore, using, I'll stop to mention that k is in the set of the integers, using mathematical induction, n cubed plus 2n has factor 3 for n in any set of the integers. So that's done, and in half the time of the previous video it shows how much easier this question really is. None of that super complex, reasonably complex factorization in the proof step. Alright, thank you, and I'll see you in math class.